My name's Robert. I'm a software engineer at Dropbox, but today I'm not actually here to talk to you about anything to do with that. I'm going to tell you about some work I did during my PhD thesis at Cornell. And we're going to explore distributed systems, really deep dive. I'm hoping to keep everything approachable to someone who's vaguely familiar with distributed systems. If you sort of lose me, I'm hoping that you'll sort of like give me an quizzical look so that I can elaborate a little more to bring you up to speed. So let's start, zoom out 539 miles high in the sky. We've got 3 data centers, and they're in different areas, and a storm can take out one of them, and now you only have 2 data centers. And how do you make your system handle that kind of event? If you only have 1 data center and the storm takes it out, there's no force on Earth that's going to save you, but if you have 2 or 3, you might be able to save yourself if you lose one. The problem is, though, that these data centers are far apart, and speed of light sort of enforces some latency on us when we're dealing with them. It's about 75 to 90 milliseconds between east and west coast. If you're on the same coast, it can be as low as 20 milliseconds, but fundamentally there's some latency there, and you're not going to get around it. And when you're working in the wide area, the latency between the data centers is the dominating cost. So a main memory reference could be 100 nanoseconds. Going on a classical hard disk, if anybody here grew up with those, it's 8 milliseconds. Round trip east-west could be 100 milliseconds. You can see there's orders of magnitude different. So no matter what you do, vTune profiling on your code, it's not going to make a bit of difference in the wake of a wide area round trip. If you can cut one wide area round trip, or even just 1/2 of that round trip, you're going to save quite a bit on latency. And there's some approaches that deal with this already. I'll go through them to sort of bring you up to speed. There's primary backup, and you'll see this in systems like Spanner, CockroachDB, practically every system that uses replication. You elect a primary, and then you have some backups that actually follow that primary, replicate from it, perhaps by log shipping, perhaps by some other mechanism. And if a client is close to the primary, that client is happy. That client can talk to the primary with low latency, get immediate reads, the writes can be immediately acknowledged, and in the background, the writes will propagate to the backup. But a client who's very far away on the other coast is going to pay a long latency cost to get to that primary. So that client is going to pay that latency cost. It's unavoidable. They can't talk to the backups that are nearby. And when the primary fails, you have to have an operator throw a big red switch to fail over to the backups. If you're lucky enough to have this automated and not have it flap and fail spuriously, you've done a good job. Most people I know just have a big red switch to fail the primary over to the backups. But that's not a free thing. That incurs an availability hit. If you say, I'm going to wait 5 minutes for the primary to be down before I fail over automatically, that's 5 minutes that you lose. If you wait 5 minutes to page someone, that's 5 minutes that you lose. And so ultimately, primary backup has this problem of availability. If you throw the switch quicker, you have to be sure that your code is robust to be able to actually handle that failover consistently. So primary backup, low latency in the primary data center. It's simple to implement and reason about. Simple being, it's simple at the basic level. Once you're trying to get into all the corner cases of making sure a switchover is really robust and fast, it becomes more complicated. But you pay a high latency outside the primary data center, and you will always have some period of downtime between primaries because there can, by definition, be only one primary at a time. There's also eventual consistency. This was very popular. I'd say it started becoming popular maybe 10 years ago, and it's becoming increasingly less popular over time, and that's a good trend in my opinion. And the reason why is you can have writes in multiple data centers. You can write locally. It'll be a very fast write. The data centers will swap and reconcile in the background, and eventually they will consistently select one version of the object and completely drop the other write on the floor. It's as if it never happened. So if you write to an eventually consistent data store and no one can ever read that write, did it really happen? It's a problem with eventual consistency, especially when you use last writer wins as the merge policy, as most systems do. All is not lost. Writes are local and thus fast, and there are ways that you can actually guarantee that you get some degree of promise out of the system. There's something called CRDTs. When combined with causal plus consistency, you get a guarantee of a merge. But data can be lost even if a write is deemed successful. So if you lose the replicas that hold the right after it's been acknowledged. No amount of eventual consistency can save you. There's also no means of guaranteeing you'll read the latest value. Even if you have the most fancy CRDT in the world that completely models your entire application as a CRDT, there's no way of saying, I am looking at the last version of this object. I'm looking at the most up-to-date copy. If you run an auction site like, say, eBay or I don't know of any other auction site, you're not going to be able to look at that CRDT and say, this represents the last state of the auction. So eventual consistency, not really a good solution in my book if you can do better. Spanner had this neat optimization they called true time. So there's still primary backup. Writes can have to go to the master, but reads can go anywhere. So the client on the West Coast here can actually use the very accurate clocks on the West Coast to take a snapshot in time and get low latency access to the data on the West Coast. So true time is fast for read-only transactions. The write path uses traditional two-phase locking and two-phase commit, just like you would find in a database textbook, if you assume that each node in the database textbook is actually backed by Paxos. But you're going to incur two-phase locking traffic in the wide area. A simple read X, write Y transaction in a suboptimally deployed version of Spanner can incur 6 or 8 wide area messages, which would be 3 or 4 round trips before the transaction can commit. And that's just read X, write it to Y. A more complex transaction than that would incur even more round trips. Then there's this trick called one-shot transactions. You'll see this often used sort of like a stored procedure. Essentially, you're replicating the code and not its side effects. So in this case, you would replicate the actual script of the transaction. This is generally a little bit more flexible for scheduling. You can schedule the transactions and then run them later. And the code can come from any data center, and you need one round trip to get it into the system that's doing the replication. But one-shot transactions are inherently not actually fully general. If you want to do something like interleave application code that does a read and then makes a decision based on that read to perform further action, you're actually going to have to break that up into multiple transactions, and then it starts to look like an optimistic concurrency control system where you'll have spurious aborts, and so you do a lot of wasted work in order to get that. So I'm going to tell you about a different point in this design space called Consus. I wanted a primary list design. The idea of primary backup doesn't really appeal to me because I don't want to take an availability hit. And since I was doing this in the context of a PhD, I get to make my own constraints. I wanted serializable transactions. I taught an operating systems course a couple times, TA'd it a couple times. And undergrads really understand that if you take a lock and you hold a lock, you basically can do whatever you want in that lock, and you don't have to worry about other people doing stuff to the same data structure, because they'll also hold a lock. You can use the same description for a database. If you type begin transaction, you run your transaction and call commit, and it commits, you can act as if you had the database the entire time. The performance may suffer horribly if you're not very good with what you do, but you don't have to worry about safety. You don't have to reason about anything else as long as what you do between begin and commit is safe. And then I wanted efficient commit. I sort of set a benchmark for myself. I wanted to get it as fast as possible. And that's what we're going to talk about today in the talk. Essentially, you can't do better than 2 message delays, because that's just send it to the remote data center, get an acknowledgement that it was sent. So that I consider that the bare minimum. 2-phase commit would obviously be 4 message delays if you can optimize it. So anything more than 4 message delays is just a waste of time. So let's go for right in the middle, 3, and we'll get there. So the contributions of this idea was a new commit protocol. So I'm going to sort of gloss over everything transactionally related except the commit protocol. We're going to walk through how that works and see how you can use proven correct consensus protocols like Paxos to actually build a bigger system. So the system looks sort of like this. In each data center, you've got a key value store, you've got a transaction manager, and you've got the commit protocol component sitting over there on the side. And this talk is entirely about that commit protocol component and how it interacts with the other data centers. There's a whole other talk that could be given on how you build a scalable key value store, a whole other talk on how you build a scalable transaction manager. The code's written, it's out there, it's in the paper that I wrote. I'm not going to talk about it today. All you really need to think about is a transaction is a log. Think about MySQL's bin log, for example. If you could take the bin log from one MySQL instance and feed it into the commit manager here, and then actually apply that bin log based on the outcome of the commit manager, you could build this system on top of MySQL. But essentially, all the commit manager does is take that log of transactions and return a yes or no decision, commit or abort. And so there's some assumptions here. Every data center running the commit protocol should have a full replica of the data and a transaction processing engine. So I'm assuming that if you have 3 data centers, you have 3 copies of your data. This is sort of realistic because if you lose one data center or want to be able to lose one data center, you have to have another data center with your data in order to remain available during that loss. I'm going to also state that the transaction manager sort of follows the traditional 2-phase commit prepare operation semantics, which is to say if it says a transaction is prepared, it can later abide by a commit decision. It won't ever say, oh, sorry, I told you I prepared it, but I didn't actually prepare it. I can't commit. So the basics of this protocol are that a transaction may commit if and only if a quorum of the data centers can commit that transaction. I'm not going to go into quorum replication here. I'm happy to talk afterwards about why it is that you can actually say that a quorum of data centers committing a transaction is sufficient. It does impose a little bit on what a transaction actually means. That's also a whole other talk. Just if a majority of the data centers can commit the transaction, though, it will commit. Like I said, we're going to execute up to the prepare stage, run the commit protocol, and then actually accept the results of the commit protocol and make them persistent. And data centers that fail to execute a transaction will actually synchronize behind the scenes to apply transactions that they missed. This can be done lazily, it can be done proactively, and it can be actually done using the commit protocol itself. There's details about that I can point you to in the paper. So like I said, today we're only talking about this red box. And if we were to take those 3 data centers and draw a timeline of the activity of a single transaction in the system, we would have the initial execution. The transaction is going to execute in one data center. And once it finishes executing at the bottom of that first green box, the commit protocol is going to begin. The initial data center will ship the log for that transaction to 2 other data centers to replay. Those 2 other data centers will play the transaction and then broadcast the outcome of the transaction to others. And so by the second dotted horizontal line, every data center will have observed the outcome from every other data center, sort of knowing whether a majority have committed. And then we need to somehow achieve consensus on those outcomes. And, okay. So here we have the consensus step. It seems sort of unnecessary, right? At the second dotted line, everybody sort of has observed the results. Why do we need a consensus step? Well, they've observed, but they haven't learned. Here I'm making a distinction that you won't necessarily find in the literature. Learning is there. Observing is a term that I'm using loosely. Observing something means that I have seen it, and I know that whatever machine generated that event has also seen it, but I don't know anything about what other people may observe. Whereas learning means that I have observed the original event, I have learned the event, and I have guarantees that as long as my system stays live, everybody else will learn the same thing. So observing is enough to say what I know. Learning is enough to say everybody will eventually know this. And the consensus step gives us the learning. So back to this diagram, if we want to count message delays, we've got 1 broadcast to broadcast the initial log, 1 broadcast to tell everybody what the outcome was within our data center. And then somehow we're going to figure out consensus in one message delay. Not a round trip, 1 message delay. And so 3 message delays equals 1.5 round trips. So to do that, we're going to take a detour through to generalized Paxos, and before generalized Paxos, we're actually going to talk about regular Paxos. And we'll see how we can use these protocols to achieve consensus in that one hop. So traditional Paxos makes it possible to learn a value. There's these different properties, and essentially these properties intuitively correspond to what you would want from a system that gives you very strong guarantees about learning a value in the face of failures. There's non-triviality. If you learn something, it must have come from somewhere. It doesn't just pull values out of the air. Stability. you can learn at most one value. It doesn't really help you if every proposed value is learned, because then there is no agreement. It's just everybody taking every other idea, and nobody knows which idea is actually learned. There's consistency, which is that you can't learn two different values, and so that goes hand in hand in stability. You don't want half your cluster learning one value and half learning the other. And then there's liveness, which is a property that says that if some value has been proposed, I will learn some other value possibly, or I will definitely learn a value and it will possibly be some other value. There's no guarantee that it will be the value that was proposed. There's just an assumption that we will make enough forward progress to actually learn the value. And this makes a few more assumptions than Paxos makes for correctness. So with traditional Paxos, we can just take that algorithm I just described and say, I'm going to run Paxos instance 1, I'm going to run Paxos instance 2, and you can run n different instances of Paxos, and what you get is a sequence of values. You get a log. So Paxos is not log replication. It is quite literally choosing a singular value. And when you choose a singular value in succession with indices, you end up getting a nice log. So that's what traditional Paxos does. And I won't go into the details of the actual protocol because they're not really relevant here. Generalized Paxos takes that and says, let's add a whole bunch of more math to that. And that generalized Paxos paper in traditional Lamport fashion has an abstract for engineers and an abstract for mathematicians, and it's very disdainful of the engineers. Lamport likes to do a lot of stuff like that in his papers. The idea here is that we want to make a partially ordered set. You can think of that like a DAG. There isn't a total sequence of values. Things are not necessarily ordered with respect to one another. So you can implement traditional Paxos on top of generalized Paxos, but you can also do much more. And it has this crucial property that a acceptor for generalized Paxos can actually accept a value and commit to accepting that value without doing a round trip through anywhere else. It can do it without any network communication whatsoever. And so that allows us to do stay on the fast path and get a one-hop agreement. So if you look here, we can see at the top of the diagram there is the traditional Paxos. When a proposal comes into a node and that node is not the leader, that node must forward the proposal to the leader, and the leader can then run Paxos to make that value agreed upon. So you have at least one network hop when a proposal comes into someone who is not the leader. And then you have additional network hops for that leader to agree on the proposal, and then you'll have additional network hops to disseminate the outcome of that learned value. And this is what makes Spanner have so many different message delays in the body of a critical transaction, because in addition to doing the two-phase locking where you have to contact a remote server for acquiring the lock, that server is then running Paxos underneath the hood to actually guarantee the durability of that lock request. Generalized Paxos, on the other hand, allows any server that's on the fast path to immediately say, I accept that value and add it to my set of accepted values, and then just broadcast its set of accepted values. And the way that works is there's some math that you can do over that partially ordered set, or the set of partially ordered sets, to learn the value. You essentially find what intuitively corresponds to what's in common between all three of the acceptors, or between a subset of the acceptors. So here, if acceptor 1 accepts the value A, that value is not actually learned by anyone because it's not common to enough of the acceptors' sets. Similarly, if acceptor 2 accepts B, it can do that immediately with no extra communication to anyone else. But it's not a learned part of the value. And acceptor 3, even if it accepts A and B, we're not yet to the point where the learner can learn anything. It's only when a suitable number, and in this case 3 requires 3, can the learner actually learn the value A and B. And A and B are not ordered with respect to one another. There's no arrow between them indicating order. So the learner can learn them, and these values can be learned in any order. It gets a little more complicated if you want to add a little more ordering to the partially ordered set, more constraints. Here you can see that acceptor 2 has accepted D before C, while everyone else has accepted C before D. The learner can't learn anything because there's no common graph in common containing C and D. There's a conflict. So when there's a conflict like this, we do have to fall back to classic Paxos. So you can see if classic Paxos changes C and D to something different, the learner can learn that value. So using generalized Paxos for Consus, we want to stay on that fast path. And it turns out that if we take every outcome from a data center, that decision whether the data center can commit or abort the transaction, or can commit or wants to abort the transaction, that's just a command in a partially ordered set. And we're going to introduce no order across them. So like A and B in the previous slide, there is no order. They can be learned by anybody in any order. The outcomes are incomparable, therefore the post sets will never have a conflict, therefore we will never fall back to the classic Paxos. After accepting an outcome, we can immediately broadcast a newly accepted state. Once a node receives enough of these broadcasts, it can run the algorithm for learning locally and actually just get the set of commits and aborts from the different data centers. Then it's just a simple task of tallying, okay, I've got a commit, I've got a commit, oh, I've got an abort, and now I've got another commit. So now I've got a majority of the data centers want to commit, I can commit my transaction, and so each data center can independently calculate the tally without communicating with a single leader or other data center. So this third round where I said we're going to magically perform consensus, that actually equates to a phase 2B broadcast for generalized Paxos. So there's a large number of loose ends here that I've completely glossed over. Garbage collection. In any Paxos algorithm, any consensus algorithm, Raft, Zab, Paxos, doesn't matter what, garbage collection is always a problem. But it becomes a bigger problem when you're collecting a part of a partially ordered set. Because what does it mean to actually take away a prefix of a partially ordered set? There's no real good definition for it. There's no real way to make a good definition for it, except to sort of move in epochs, where you add a new node that is totally ordered above everything already there, and then throw away everything before that node. And then you're sort of degrading back to classic Paxos. So I'm going to sidestep that issue entirely. A transaction that comes into the system starts a new instance of generalized Paxos for the commit protocol. And when we can garbage collect the temporary state for the transaction, we can just throw away every bit of state for generalized Paxos. You're talking even 40 data centers if you're one of the largest companies on Earth. That's a couple hundred commands. You're talking kilobytes to megabytes of disk space used to persist the state for the generalized Paxos garbage. That's not much garbage at all, and it's proportional to the number of active transactions. There's also the possibility for deadlock. So I'm hoping that people in the audience were sort of rolling their eyes when I rolled out generalized Paxos, because it seems like a very heavy-handed tool to deal with transactions. Why not just make a custom protocol that can commit things? I actually tried to do that, and after a month or two of sitting there running hand-drawn protocols, every single one of them had a problem where if there was a deadlock across data centers, it would not be able to make progress. And you can get into a deadlock situation very easily. Imagine you have 3 data centers. Each data center wants to read a value and write it to X. And they just so happen to be reading and writing each other's values. Those 3 transactions in the wide area are going to need to be ordered with respect to one another. You can't commit all 3 of them. And so if each one starts its initial execution in a different data center, that data center is going to vote to commit the transaction that originated there and abort the others. And now each one is left with out sufficient thresholds for committing, and you can actually get into a deadlock situation, especially if you have only 2 transactions that are doing this. So to sidestep that, I want to introduce the notion of a deadlock-induced abort. So if the local data center detects that there could be a deadlock, it can actually add to the generalized Paxos set a command that says, I would like to retract my commit and change it into an abort. And here's where the power of the partially ordered sets shines through. If you make that command totally ordered with respect to everything else in the system, that will be learned by everybody else in the same order. So there's no worry about one data center seeing the retraction from an abort, from a commit and changing it into an abort, and another data center not seeing it and then committing the transaction accidentally. Everybody will tally in the same way. Because the abort due to deadlock command is totally ordered with respect to everything else, if you topologically sort the DAG corresponding to the POSET, what you'll actually do is commit, up, abort. Oh wait, there's a commit that moves to an abort. And it doesn't matter if you do abort, commit, or commit, abort, commit. No matter what order you process the first 3 commands, the 4th command will be the one that moves the tally from one column to the other. And at that point, the total number of commits and aborts will always be the same on every machine. And it can say, oh, well, we've actually already got a threshold for commit. We will just ignore the deadlock-induced abort, let the transaction commit. That's just the same as aborting it due to deadlock, because now it can resolve the lock contention, get it out of the system, and keep making progress. There's also a performance problem. The generalized Paxos algorithm, I believe, is like 20 pages of TLA plus, and it's very heavy math, and everything's specified like there exists some Q such, or some value V such that there exists some quorum Q such that there also exists some quorum R where Q and R have this property of relating to each other. It's this huge mess that the only way to really solve it is to enumerate every possible value that you could learn and see if they pass the check. And of course, since you want to learn the maximal value, you really do need to enumerate all of the values. I haven't found any algorithm that does better than that. Programming language literature, they're all like, oh, we never actually want to compute these values fast. We don't care if it takes overnight to prove our theorems, but when you're working in a system that's running real-time transactions, if it costs you 100 milliseconds of CPU time to actually decide whether you've learned anything, just to be able to save 100 milliseconds of latency, you're making a horrible trade-off. So I had to spend quite a bit of time optimizing the implementation here. It turns out that there's quite a bit of pre-computation you can do before you ever run the learning algorithm, and then the core of the learning algorithm can degrade into a bunch of bit operations or counts on arrays. So you can actually get by doing quite a bit of work without having to run actual graph algorithms, without actually having to enumerate every single possible value. And so that was a big hurdle that I had to overcome. There's also a lot of Paxos that I didn't talk about here. It was sort of a personal challenge of mine to see how many different ways I could use Paxos in the system differently. There are 4 to 5 different implementations of Paxos here. This sort of came up because someone at Cornell mentioned to me that Raft was easier than Paxos, and I thought Paxos was rather elegant and easy to use. So I have 4 or 5. It started out with 5, and one of the optimizations optimized away so much that it would be almost slanderous to call it Paxos. So there's a client as leader optimization where we simply select the ballot once, and the client will lead the transaction forever. So within each data center, that transaction manager that I showed you earlier is actually a replicated state machine. For each transaction, the client's write-ahead log is logged to 5 different servers. And those 5 servers maintain a replicated state machine. That log is durable. One of those servers can just drop off the face of the earth. The client can talk to the others and keep pushing the log. And there's the insight here that the log of the client and the client itself are fate shared. If the client just dies and stops issuing commands to the log, it doesn't matter that the log can still accept commands because it's only accepting them from the client. So we can make a whole bunch of optimizations there. There was Gray and Lamport's Paxos commit. Essentially, the idea here is that those 5 different servers are logging the commands from the client, but they're also doing interactions with the key value store and the rest of the system, acquiring locks and so on. And they need to be able to say, yes, I have done all of the requisite work logged by the client. And that's not something that they can easily do logging into the client's log, even if there were others who could submit commands to that log. Instead, what they do is they each have a singular value of Paxos. It's a single value. It's not a multi-value thing like I showed before. It's a single synod algorithm, as they call it. And each one will log their desire to commit or abort. And if a majority of the nodes that are running a client's log vote commit, then it can proceed to the global commit algorithm. There's also the generalized Paxos implementation I described here. It's fully general as far as I know, save for garbage collection, so you could rip it out and use it for your own stuff. That has a problem when run in the wide area, which is if you were to lose one machine, that machine dropping off the face of the earth then means that data center appeared to drop off the face of the earth. I don't want a single machine failure making it look like an entire data center has failed. So every acceptor in generalized Paxos for the data center level algorithm is actually its own recursive Paxos state machine. So the Paxos state machine is actually agreeing upon the commands and messages to feed into the next Paxos state machine. So there are 5 servers sitting there running Paxos to agree upon the commands to feed to the acceptor running Paxos. And you can get even more creative than that, making a generalized Paxos state machine so that the messages can go to the different state machines in different orders. And now you're left with a state machine or a machine in a single data center that appears to be this really, really robust machine, but it's actually 5 machines, and no one machine can take that system offline. No one machine being slow can cause that system to lag. There's no leader to have die that you then have to wait to reassign. In the average case, there's always pathological cases where you can force an availability hit. But in the common case, you won't take an availability hit, even if you just go up and pull out the power cord for a machine. And finally, there's a system called Replicant, which is a replicated state machine hosting service. So you can write just straight line code, C, C++, anything that compiles into an ELF binary, but it doesn't have to be that. You could talk over, it talks over a pipe, so anything that can read and write over a pipe would work. So you write single-threaded code, and then you make RPCs from your client library. And it will automatically run the code on 5 different machines or 10 different machines, and feed it the RPCs in the order of the client's calling. So you can actually do things like cluster membership. I don't know if anyone here has ever played with Zookeeper and looked at the recipes for locking algorithms, and then looked at the changelog for the recipes for the locking algorithms to see how many times it's been revised in response to a race condition. It's really hard to write that kind of code. I don't want to have to write that kind of code. Instead, I write code that says, oh, I am registering new server S1, and it's in data center US East. I can add that server. I can now assign it to these Paxos groups, and I can publish a new config, and everybody waiting on the condition variable for that config will get woken up, receive the new config, and be able to apply it. So let's look at how it actually performs, because there's always the question is this thing real? And the answer is yes. It's currently approximately 32,000 lines of code. Since I've started employment, I haven't actually made it grow much. There's another 41,000 lines of code I stole from Hyperdex, and it's released under an open source license. The code's not production ready, but I did make sure that every write to disk is actually durable like you would expect. I did make sure the failure paths are implemented. They just aren't really well tested, so I wouldn't deploy it in prod. To evaluate it, I went and got a bunch of AWS EC2 instances, and I did something peculiar here. I picked them in the same availability zone, and then I added an artificial RTT between them. And I did this because I wanted to minimize the effect of network variance. In the same availability zone, the variance is going to be on the order of single-digit milliseconds, and I'm setting a 200 millisecond RTT, which means that I can be pretty sure that everything I'm measuring is a result of the RTT of the system and not an artifact of an experiment that's just running in an adversarial network condition. And then I had one server that ran against the deployment, and that server actually would use a different, or could use a different node every time. There's nothing that forced it to do so, but it could actually send the transaction to a different data center every time, and I believe it was configured to do it at random. And so what I did is run the TPC-C benchmark, which is sort of if you were doing a warehouse in SQL in the 90s, this is how you would build it kind of benchmark. There's 10 hot keys on which everything contends. And what I did is I ran that in just one data center. I used just one of the 5 nodes I had deployed and ran the benchmark against that. And I got the line on the left. Then I took that, doubled it. Remember, we're going to execute twice within Consus, and added 300 milliseconds, which is 1.5 RTT in our simulated environment. And then I measured 3 data center and 5 data center performance. And here you can see we fall just short. That's actually a predictable event. Number 1, by doubling the CDF, you're actually making the long tail much worse. Number 2, when you're replaying a transaction, you're actually playing the operations in parallel. The first play of the transaction is actually pulling into the client, reads and writes, and the client is issuing the writes back. So there's going to be higher latency there. What looks like an anomaly toward the bottom is actually a result of TPC-C requiring 1% of transactions to abort. A transaction that aborts instead of calling commit just terminates in the local data center. There's also a whole bunch of other workloads that look sort of like the previous graph. The only one that's different and interesting is the stock level workload. So here you can see the CDF again on the far left. There's the red line, and that's running in one data center. On the far right, we have the long dashed line, and that's what we would expect. And in the middle, you can actually see the 3 and 5 data center cases. And they're very close in performance because the number of data centers does not actually influence the latency of a commit. They are significantly less than what we computed the latency would be because the stock level transaction is actually reading about 200 different keys. So here you can see the effect of the serialized execution versus parallel re-execution or replay. So to summarize today, I've sort of shown you what can be done for geo-replicated transactions. You can make them with lower latency. Not everybody necessarily wants to pay a cost on a write to go to a remote data center, but if you're willing to pay that cost or are already paying that cost, you can actually get masterless geo-replicated transactions. Paxos is not a one-size-fits-all algorithm. I've tried to show many different ways you could use it. And I think the biggest lesson I'd like you to take away from this is if you start with a careful specification of your fault tolerance and availability requirements, it's going to sort of force you to think about the different ways you can navigate the design space. If I were to take away that requirement that I must be available all the time no matter what happens, so long as a sufficient number of servers don't die simultaneously, there's a lot more that could be done. You could have a much simpler algorithm, you could have a much simpler protocol, but you would be taking an availability hit sometimes, and that's up to you whether you'd like that. And so I have about 3 minutes left. I don't want to take public questions, but I'm happy to take questions up at the front, and thank you.